Hello, my name is Marta, and in this video I will explain sums to infinity. We'll focus on geometric sequences only. So this lesson will be only about geometric progressions. You already know what it is, and you know that to find the sum of the first n terms of a geometric progression, you can use this formula, where a is the first term in a geometric sequence, the first term, r is the ratio, the common ratio, and n is the number of terms that you want to add. So, for example, if I want to add n terms, it means that I'm adding a1, the first one, the second one, the third one, and then I continue adding until the nth term. And using this formula, you already know that you can find the sum. So you can find the sum of the first 10 terms, 20 terms. I'm not gonna go into detail. It was discussed in a previous video. But now I would like to add, and never stop. So I want to find the sum to infinity. Is it even possible? And if yes, how to find it? I will give you two examples because I know it's a weird concept. If it's the first time you want to find the sum to infinity, I can imagine that it's really hard to imagine what we're trying to do here. Because obviously the first example that comes to my mind is any geometric sequence, let's say 1, and I create the series, so I'm just adding the terms of a geometric sequence. Let's say the geometric sequence of with the first term 1 and then the common ratio is 2. So each term is twice as much as the previous one. Right, so if I'm adding those, then, I mean, if I'm adding these terms, then obviously, since the ratio is 2, so each term is even bigger than the previous one. So every time I'm adding, building up a bigger number, right? So S1, so the sum of the first one term, so just the first term. Then S2 is the sum of the first two terms, so 1 plus 2, that's S3. Then S3 will be the sum of the first 3 terms, so that would be 7. S4, 15, S5, I add 16 to that, and S6 is the sum of the first 6 terms, which is 63, and so on and so on. The next term will be even bigger, as the 7th term is 64, I add to that, my sum gets bigger. Yeah, and well, this series is divergent. But now let's take a look at the next example. Let's say that the first term in a geometric series is 1, but then the ratio is a fraction. So to create the next term, I multiply by half, then the next term I multiply by half, that's 1/4. The next term I multiply by half to create the next term. The common ratio is half. Well, now the situation looks completely different. S1, so the sum of the first one term, so just the first term is 1. S2 is 1 plus half, that's 1.5. S3 is 1 plus half plus quarter, that's 1.75. S4 is add 1/8 to that, so that is 1.875. S5, so the sum of the first 5 terms, I will just cheat, I calculated it before. So this is 1.9375, and then S6 I also calculated before, so I just added up those 6 numbers, and that's 1.96875. Now the situation is totally different. If I want to find a 7 now, I will add even smaller fraction. I will add the 7th one, so 1/64, and I will keep adding the numbers which keep getting smaller. And actually, maybe you can guess now that as n approaches, as n tends to infinity, Sn tends to a limit, to a particular number. These sums are getting closer and closer to 2. So that's the limit, and this time it is a convergent series. And this limit we call the sum to infinity, and I guessed that it is 2. but I will show you how to calculate it as well. So that's just the two examples just to make you realize that yes, the geometric series are sometimes convergent, but as the white one, but sometimes they are sometimes divergent as the white one, and sometimes convergent, because these sums, as we get more and more terms, and the terms are actually smaller and smaller, those sums are actually tending to a limit. So that's the observation I wanted you to make. I just wanted you to realize that there are two options. And now going into details, I will use this formula, the formula for the n terms, and just observe what happens with this formula as n tends to infinity. So we have the sum of infinitely many terms. Let me copy it somewhere. Oh, maybe here. Actually, I have space here, so I'll just do it here. Sn is a1 minus r to the power of n over 1 minus r. And basically, if the common ratio r is a fraction, so it is a fraction between 1 and minus 1, for example half as it was here, then as n tends to infinity, r to the power of n, this thing here, r to the power of n tends to 0. Imagine with half. If you get a bigger and bigger power of half, your result is smaller and smaller. In general, if you have a fraction between minus 1 and 1, the bigger power you get, the closer to 0 you get. And then, if this tends to 0, then that means that Sn tends to just this is left, because r to the power of n is 0. So that's basically a times 1, so just a over 1 minus r. So if the common ratio is a fraction between minus 1 and 1, as n tends to infinity, r to the power of n tends to 0. And then the sum to infinity is a over 1 minus r. So this is the formula we have to remember, and that happens for r between minus 1 and 1. But if r is a number which is, say, if r is bigger than 1 or r is smaller than minus 1, then, well, for example, in the white one, when r was 2, the r to the power of n will get bigger and bigger if r is 2. So r to the power of n doesn't tend to 0, and these series with r which is greater than 1 or smaller than minus 1 will be divergent. So the sum to infinity will not exist. And then we just say that the series is divergent, and we don't calculate the sum to infinity. So that's all you have to know for now. Let me just scroll down and write it clearly somewhere here. Okay, so if the common ratio is between 1 and minus 1, then the sum to infinity is a over 1 minus r, where a is the first term. If the common ratio is bigger than 1 or smaller than minus 1, the sum to infinity doesn't exist, so this series is divergent. That's what we have to know for the sums to infinity. Since I know this formula, I can come back to my example that we started with and where we guessed the sum to infinity, which was not really nice. We shouldn't guess, we should calculate. Right, so in this example, in the example I gave you at the beginning, before we knew the formula, we had the geometric series with the first term 1 and the common ratio half. So now you know that since the common ratio is between minus 1 and 1, the sum to infinity is the first term over 1 minus r. Let's substitute what we know to check how much we will get. The first term is 1 in our case, and r, the ratio is half. Let's substitute. So I have 1 minus over 1 minus half, and that is 1 minus over half, and that is 2. Okay, so I guessed right. Oof. Okay, but we shouldn't guess. I just wanted to show an example because I hope if you have an example you understand better. But when you actually want to find the sum to infinity, you should use the formula, not guess. And that would be it for this video. See you in the next one.